Welcome to the video on solubility and solubility rules. Your narrator is me, Jim Hart, and I'm going to focus in on using solubility rules to determine if an ionic compound will dissolve in water, or if we bring ions together, whether they will make a solid and fall out of solution as precipitate, or they'll just stay in solution. In order to do that, we need to know how to interpret solubility rules, and that's what we're going to use this video for. There are a lot of factors that go into determining if a particular compound, an ionic compound, will dissolve in water or not. I'm going to list them here and show you a picture showing the interactions that are present, but we really don't have the tools to use those things alone. That's where the solubility rules are going to come in later. Let's go ahead and just list the main factors that are important when something dissolves in water. You got the attractions among the ions in the solid, the attractions between the water and the ions in solution once they go into solution, and the temperature also plays an important role. The chemistry concepts behind some of these things, ionic attractions we have talked about when we talked about naming. Ionic compounds, we talked about Coulombic attractions and a little bit about what's holding ions together in an ionic compound. The attractions between the water and the ions in solution, we've had little bits and pieces of this, but really not the whole picture of the attractions between ions in a polar molecule like water. So we're getting out into an area where we don't have a really strong background, so it would be impossible for us to use just our chemical knowledge to make predictions. And the same thing is true about temperature. We mentioned temperature a little bit. To study it properly, we'd have to go into the field of chemical kinetics, studying rates of reactions. So thank goodness we have solubility rules to help us out. Let's go ahead and just look at some pictures, get an idea what's going on in solution. You drop a chunk of salt in water. On the particulate level, what you have is a solid, the ions being attracted to each other, plus minus. You got the ions in solution interacting with the water molecules. So in the solid, you've got the Coulombic attractions, and in the liquid, you've got the attractions between the charged particles and the water molecule, which is a polar molecule. And so very complicated. Even an experienced chemist would have a hard time without more information predicting if a particular ionic compound would be soluble or not. And that's really where the solubility rules come into play. Something called solubility rules. And here's a typical list, what they usually look like. It's tables of information that are based on experimental observations. And how they're organized, this is a typical list, maybe just like the one in your textbook, it may be different. Listed as what are usually soluble and usually insoluble, kind of separate them out, and start out with some cations that have rules. But notice that that's the only one that has anything to do with cations. All the rest of them are anions in the left-hand column. Some cations are mentioned in the right-hand columns for those things. So these types of things are important. You don't have to memorize them all, although it's suggested that you do memorize the rules for the ones with no exceptions, and that would be in this box I'm drawing here. That if the compound contains any of these ions, then it's going to be soluble because there aren't any exceptions. The rest of the rules, you don't want to try to memorize them. You want to be able to look at your formula, look at your name of the compound, look at the rules, and then use them to determine if the compound is soluble or not. And the reason for that you don't want to memorize all the rules is because different sources will have slightly different rules. There are different cutoffs. You put a solid in water, and if a certain amount of it goes into the water, then people make a decision. If more than a certain amount dissolves, it's soluble. If less than a certain amount dissolves, it's insoluble. And in different circumstances, those numbers, those values are different. So it's important to be able to use the rules, not so important to memorize them. more detail about how they're usually organized. The cations, again, just the alkali metals, and make sure you distinguish the difference between alkali metals and alkaline earth metals. Group 1A is, those are the alkali metals. Group 2A are not covered by this rule. They are alkaline earth metals. So the only thing that's covered by that cation rule are the alkali metal ions, and the ammonium ion is included along with them. All the rest of these are anions, and any other cations are listed as exceptions only. And that really plays a big part in how you're going to use these rules. You're going to find the cation and the anion and apply the rule as follows. Let's look at how you do apply the rules. So first step, determine the ions, and that goes back to your naming. See how important it is. It keeps rearing its ugly head. If you didn't master naming and writing formulas and writing names from formulas and formulas from names and figuring out what ions are in a formula, you need to go back and review that. That's the starting point for so much of what's coming in chemistry from this point forward. So once you've determined the ions, then you're going to apply the rules. If you've memorized the ones that are always soluble, if it's one of those things, you can already be done. But if you need to look at, it's not one of those things, you need to look at a particular combination, you need to find the rule that applies. And don't forget to check the exceptions. And once you have found the rule that applies, you are done. You don't have to go find anything else. You're done using the table. So if we want to determine if something is soluble or not, these are the steps to take. Now let's apply those to two examples. Sodium carbonate. Well, I just named it. I'm using that skill. I'm determining the ions in the compound, both in name and formula. Because if you see this table, it's kind of a mixture of names and formulas, and you'll find that often that people do that. So you need to be able to know how to name things, write formulas for the ions, write formulas for the whole compound, write names for the ions. All of these things come into play. And if I have memorized the ones with no exceptions, I could be done. But let's go ahead and just go through this. And I start at the top, and sodium is an alkali metal. There's the rule right there in the top of the table, and there are no exceptions, so that means that sodium anything is going to be soluble, and this is sodium carbonate. It is soluble too. So stop, you're done. We determined that sodium carbonate is soluble. I'm not going to go try to find the list down the list and look at carbonates. I don't need to. Silver chloride, second example. Well, I just named it. I looked at AgCl and immediately thought silver chloride, and that's what you should be practicing yourselves. That saves a lot of time and effort. We spend a lot of time covering naming, and this is where you're using it. So use that skill you've got. Write the name and the cation symbol, the name and anion symbol, silver chloride. So the cation is silver. That doesn't have a rule, but chloride has a rule. It's the anion. I go down and find the chloride rule. There's the chloride rule. Now look to the right. Find silver. Is it in the list of exceptions? And there it is. It is listed as an exception. So while most compounds containing the chloride ion are soluble, there are some exceptions. Silver ion is one of those exceptions. That means that silver chloride is not soluble. It is insoluble. So stop. We just determined it. You are done. I'll give you. So I'm going to use the Thinker Buddy here. Let you try to apply these rules. Determine, are these things soluble or insoluble? And go ahead and pause it and restart when you're ready to continue. The first one is magnesium chloride. Magnesium is an alkaline earth metal. There's no rule for that. I have to go use the chloride rule again. Should have figured out that the rule tells me that most chloride containing compounds are soluble, and there's no exception for magnesium listed, so therefore magnesium chloride is soluble. Barium sulfide, the second one. I have to find the sulfide rule once again. Barium is an alkaline earth metal. There's no rule for it, so apply the sulfide rule. Usually insoluble, but I see that barium is listed as an exception, so it is soluble. And slightly is mentioned in the rule, so I can add that information too. Notice I'm not determining that myself. I'm just reading it from the table. Iron 3 carbonate. All carbonates are insoluble with some exceptions. Iron 3 is not one of the exceptions. Lead 2 nitrate. I wouldn't have to consult the table if I had memorized the ones that have no exceptions, because nitrate has no exceptions. All nitrate containing compounds are soluble. Same thing is true for the ammonium hydroxide. Ammonium ion is there, soluble. Same thing's true for potassium phosphate, soluble because of the potassium ion. Copper 2 hydroxide, I have to go to the hydroxide rule. And I find that it's all hydroxides with some exceptions are insoluble. There's some exceptions there. Copper 2 is not one of them. So that's why it's insoluble. So if you made any mistakes in doing this, go back and try to do it some more. You just write out the ions, find the rule that applies, apply it, and you're done. Don't make the mistake of confusing an alkali metal with an alkaline earth metal. That's really the only problem some students run into. I think we're ready to move on to the precipitation video. So precipitation reactions and net ionic equations for precipitation reactions. This is where you're going to use the solubility rules that we've just gone over. So make sure you have a pretty good understanding on how to interpret a solubility rule, and then you'll be ready to continue on.